Hello again, it's me, Professor Aaron Albert, here with Lesson 9. Let's learn some econ. So, today we're going to work on our last of the usual suspect functional forms. That is, we're going to show you how you can think through utility maximization with quasi-linear utility. This is important because quasi-linear utility functions, the only one that could either have a corner solution or an interior solution, not strictly one all the time. Also, we're going to show you how, using the same tools we've been using to solve for utility maximization, we can solve expenditure minimization, and you'll recognize pretty quickly that it's basically the same exact thing, just a little different. So, remember, anytime you're maximizing utility, you should be able to just apply the Lagrange optimization method as long as your utility function gives you indifference curves that are convex, don't cross either axis. If that's the case, just use the Lagrange method and find a nice interior solution. If you're ever encountering a utility function that is either not convex, not differentiable, or the indifference curves do cross either axis, you still might be able to get away with the Lagrange method, but you should definitely check for corner solutions. That is, try zeroing out either of the goods and see if that makes things better. Although, going through this process guarantees you'll be able to find a solution every time. It's a lot easier than it sounds because, for the most part, we'll just be using our familiar forms. As long as you quickly recognize that you have Cobbs-Douglas, or you have substitutes, or complements, or quasi-linear, just apply the appropriate methods for that function, and you're good to go. So, you'll remember quasi-linear was interesting because it is concave up, that is, it is curvy everywhere. It is differentiable everywhere. However, it violates the last red flag, namely, it has the potential for corner solutions because the indifference curves do cross the x and y axis, and therefore we might not have tangencies for an interior solution, right? Like this budget line is not tangent to any indifference curve in the interior of this quadrant of this x and y axis. So let's work one through and just see what happens. So let for a minute utility be given by 4 root q1 plus q2. Let's let our budget be given by, we have $10, good 1 costs $1, and good 2 costs $2. Take a moment, refresh yourself, write down the Lagrange function that would give us the maximization of this utility function subject to our budget, find marginal utilities 1 and 2, ask yourself what these marginal utilities mean, find MRS and MRT, and after that, roughly draw some indifference curves and see what you find. So, note first that our MUs are very easy to find. MU2 is just 1. MU1 is just DQ this, DQ1. Bring the half down, we have 2Q1 to the negative 1/2. Hey, check, it worked. If we divide that by 1, we still get 2Q1 to the negative half. And MRT is just going to be the negative ratio of our prices, namely negative 1 over 2, so negative half. We know that when you solve the Lagrange method, the first two first-order conditions will simplify to MRS equals MRT. Therefore, we know it must be true that 2Q1 to the negative half equals negative 1/2. If you work that out, you'll find that that means Q1 must equal 4 times 2 squared. That is, Q1 must be 4 times 4. Q1 must be 16. So then, work out for yourself, what is the equilibrium quantity of Q1 and Q2 if we believe the Lagrange method has given us something useful? Well, if it's interior, Q1 equals 16. How much does Q1 cost? Well, 16Q1 would cost me $16. I only have $10, means I must have negative 3Q2. That doesn't make a lot of sense. We cannot afford 16Q1, so that means we must have a corner solution. And actually, this Lagrange method did give us something useful. It told us that Q1, until we have 16 of them, is a very appealing option. So let's see why. First off, we saw using substitutes that looking at the marginal utils per dollar was very informative. Our marginal utils for good 1 is 2q to the negative half, and its price is 1. So our utils per dollar is just 2q1 to the negative half. What's your marginal utils per dollar for q2? Well, that's just 1, i.e. dq2 dq2, divided by 2. So half. So that means we're going to get better bang for our buck from good 1 than we are from good 2, so long as 2q1 over half divided by 1 is greater by a half. That will be true as long as q1 is less than or equal to 16. So until we can afford 16q1, what should we do? Just dump all our money into q1. How many q1 can we afford with the current budget? Solve it out. Well, with $10 and each q1 costs me $1, it looks like I can get 1 times 10, 10 units of q1. If I have 10 units of q1, how many units of q2 can I buy? That's right, 0 units. So my solution to this problem is just, well, q1 gives me better bang for the buck until I can afford 16 of them. I cannot afford 16 of them, so I should just spend all my money on good 1. Let's change this one slightly. Solve it again, but this time let your y equal to 25. Again, what is MRS, what is MRT, and what does it suggest the solution should be? You'll note, just as before, the Lagrange method would tell us that MRS equals MRT and that Q1 equals 16. If Q1 equals 16 is the solution to the first two FOCs, what does that suggest regarding how many Q1s and Q2s we should buy? Well, 16 Q1s will cost me $16. If I have spent $16 in Q1, I have $9 left. That seems completely reasonable. So we should just buy 16 Q1, spend the rest of our money in Q2. As long as we have 16 Q1, after that, we're more cost effective to put our money into good 2. Remember, we said that Q1's the better deal because MU1 over P1 is greater than MU2 over P2, so long as Q1 is less than or equal to 16. So every dollar we spend after the 16th dollar, we should put into Q2. So we'd get 16 Q1 and 9 over 2 Q2, a reasonable interior solution. So this basically shows you the two ways that quasi-linear budgets can go. Either we have an interior solution, and our Lagrange method gives us a reasonable non-negative value for both goods 1 and good 2, or we have a corner solution. We really like one of the goods, and we don't have enough money to suffice ourselves in it, so we'll spend our entire money on whatever good is suggested that we cannot afford enough of. The reason this is because one good will always have higher marginal utilities per dollar for low values. And intuitively, this is just saying we will buy whatever good has a non-constant marginal utility per dollar, so long as its marginal utility per dollar is a good deal. After we reach that quote-unquote good deal point, just buy the other good. How do we find that good deal point? Well, that's what the MRS equals MRT did for us. You might ask, well, this quasi-linear stuff seems kind of wacky. When do people use it? It's often used by economists when they want to talk about kind of bare necessity goods, like toothpaste. That first tube of toothpaste gives you a lot of utilities per dollar. Toothpaste is cheap, and it keeps you out of the dentist's office where they would obliterate your teeth, and that sounds really unpleasant. However, think about your expenditure on toothpaste. If toothpaste gets cheap, do you get more toothpaste? Not really. If my income goes up, do I buy more toothpaste? Not really. You just need enough toothpaste. But if you don't have enough toothpaste, you better find money to get more toothpaste. So the next thing we should work on, now that we've decided we can solve the 4 usual suspects, is how do we solve a slightly different problem? Do you go to the grocery store and maximize your utilities? Do you go and say, I'm going to spend every dollar I have, buy as much of all the right things, and I'm going to leave this store as happy as I can? Or do you do something different? Right? Imagine you go to the grocery store. How do you know how much to buy? How do you know what to buy? describe it to yourself, the shopping action you usually do. So, I think for the most part what we do is we go to the grocery store and we say, how much do I need? Well, you could think of this as being just kind of a reverse optimization problem. Say, I go to the grocery store, let's say we have a very simple grocer and only bananas and milk. I have some utility function over the bananas and milk as before. Bananas and milk have prices as before. And let's say, well, I don't need to spend all of my money. I just need to spend enough to get 20 utils. If you know you need 20 utils, how would you go about getting that 20 utils? Well, you'd probably try to do it as cheaply as possible. Why? Well, that'll leave you money for tomorrow. So, think this through. If you're going to the grocery store, you want to spend enough to get yourself 20 utils, but you also want to spend as little as you can. What function are we maximizing or minimizing? And what is our constraint now? Think it through. Well, it sounds to me like we're minimizing our expenditure. That is, good 1 costs me $2, good 2 costs me $2. I will in total spend 2 times however many good 1 I buy, plus 2 times however many good 2 I buy. I want to minimize how much I spent, so that's minimizing 2p1 plus 2p2. And I want to do that so long as I have enough utils. How do I have enough utils? Well, because my util function will be at least the 20 I've said that I need. Can we solve this? I guess, first off, let's think, can we solve this as written? Is this a well-defined maximization problem with inequality constraint? No, as before, the greater than or equal to 20 is kind of wacky. We'd have to check equals 20 as well as all the different combinations of Q1 and Q2 that give me slightly more than 20, and hopefully that's enough. However, we can just assume that it equals 20 for a couple of reasons. First off, do we know that there are values of Q1 and Q2 that do equal 20, that we're not going to jump over it on our way? Yes, we know that because these are continuous functions. We can dial Q1 and Q2 continuously until we hit exactly 20. Next, we know that in optimum, we will not purchase more goods of Q1 and Q2 than it takes to reach exactly 20, because the goods aren't free. Imagine for a minute that you have some Q1 and Q2 that gets you, let's say, 21 utils. Well, we know that there is some combination of Q1 and Q2 that is strictly less of Q1 and Q2 that reaches 20 utils. And since we've said that Q1 and Q2 are not free, we know that that costs less money. So it does a better job of minimizing our expenditure function. So this problem sounds very solvable. It sounds actually quite similar to our utility maximization problem. However, we should take a moment to make sure we actually do know how to solve this. Well, the first step is, what is our Lagrange function? Take a moment, write down a good Lagrange function for the minimization problem we just described. So, hopefully you came up with something like this. We are minimizing our expenditure, given as thus, subject to our constraint that our utility must be at least 20 units of utils. Now that you have your Lagrange function written, what would you do next? That's right. You'd write L1, L2, L3. And we take the derivatives. Derivative with respect to good 1 is what? You find it. 2 plus C times du dq1 equals 0. For good 2, do the same. What would you get? 2 plus C times du dq2 equals 0. And for the third one, it would just be the equality constraint that we are solving subject to. So u equals 20. You will note this looks a little different than what we did before. Namely, we have linear stuff in the first half, and the functions of our utility function in the second half times the constraint. But it's going to do the exact same things you found when we did this for utility maximization. Namely, these two equations are going to tell you that MRS equals MRT. Then you're going to take these MRS equals MRT, which will be some Q1 equals function of Q2, plug those into your constraint, get Q1, get Q2, and you're done. So we could go through and find these FOCs and algebra it out like usual, but I'm going to tell you we don't need to do this. We've done this 100 times. It looks like a different problem, but it's actually the same as our utility maximization problem. The method will be exactly the same. We should take a sidebar here, though, and note that this is actually pretty cool, because not only does this look very similar to our utility maximization problem, however, they actually are closely related and actually directly linked. Imagine for a minute that you've solved above. You've found some, let's call it Q1 star and some Q2 star that solve this. That is, Q1 star and Q2 star are the optimal Q1s and Q2 that minimize this expenditure function subject to us spending only $20. Next, let y double prime, just some number, we don't know what it is yet, let that be Q1 star times P1 plus Q2 star times P2. That is, let y double prime be how much money we spent in the first problem, how much money we needed to spend minimally to reach 20 utils. Well, the reason this is cool and this is magical is because Q1 and Q2 star will also solve the utility maximization problem of maximizing this utility subject to our y equaling this y double prime. That is, if we maximize our utility subject to the budget equal to the expenditure we found when we minimized our expenditure subject to minimum util, you get the same exact solution. These Q1 and Q2 star solve both a minimum expenditure problem subject to some util, as well as a utility maximization subject to budget problem, as long as we scale our budget and our expenditure properly. So the best way to get good at things is usually to practice it. So for the rest of your time today, you should work on the following expenditure minimization problems. For each of the following, do this. Write the correct Lagrange function. Give quick doodles of the indifference curves and the expenditure. If it's hard to draw, at least tell me if it's concave or convex, and if you think the utilities cross either the x or y axis. The best way to tell this is see what happens to your utility values if you plug in 0 for Q1 or Q2. Can you have non-zero utility with 0 Q1 and or 0 Q2? If so, it crosses an axis. Next, find the conditions for the solution. That is, either find the first order conditions and say that this will work. You don't actually need to work the FOCs to find Q1 and Q2 this time. It would take you a lot of time, and it's mostly just algebra. If you do not think that FOCs will give you anything useful, tell me why, and then tell me what conditions must hold for the corner solution. So either tell me that you think the FOCs will work and why, or tell me the FOCs will not work and why, and then find what alternate solution you should try. Our three utility functions given as thus will be slightly familiar for some of them and maybe not familiar for others. We're going to look at the square root of Q1 plus Q2, the minimum of Q1 and 2Q2, as well as the product of Q1 and Q2 to the 6th. For all three, let P1 be 1, P2 be 2, and note that you need 20 utils. Work on those and come back. All right, so this one, hopefully you figured out, but admittedly might have given you some difficulty. First thing we should know is this likely to have an interior or corner solution? How can we check? Well, can I have positive utility if I zero out Q1 or Q2? Yes. If I zero out Q1 and then put a bunch into Q2, I still have utility. Similarly, if I zero out Q2 and put a bunch of money into Q1, I still have positive utility. This is actually just a manipulation of perfect substitutes, and we can solve it like it's perfect substitutes. If you didn't figure this out before, pause a minute, pretend this is perfect substitutes, and tell me what you'd do. Well, note, the Lagrange method is not going to help you because we are working with perfect substitutes and we have straight lines. and we are not likely to find informative FOCs. So what instead should we do? Well, we should find which good 1 or good 2, gives us the most marginal utils per dollar. Well, good 1 gives us d this dq1 for $1. Good 2 gives us the same thing, but costs $2. So which good looks like a better deal, good 1 or good 2? Yeah, hopefully you're buying good 1. So what will be your solution? Well, we have 20 utils that we need. How do we get 20 utils from this function most cheaply? It looks to me our solution should be where 20 equals root q1, i.e. q1 equals 20 squared. Then how many units of q2 do I buy? q2 equals 0. Done. All right, let's work on this one. Have we seen this before? Is calculus likely to be helpful in this case? Now this is perfect complements again. Is calculus helpful with perfect complements? No. We have a min function. You can't take derivatives of this. Trying to find FOCs will just result in massive brain pain. What should we do instead? It must be true that q1 equals 2q2. Right? We've said that the guts of this must be equal. Second, we know that we need 20 utils. So 20 must equal the min of q1 and 2q2. So that means we know that we need to set q1 equal to 20 and 2q2 equal to 20. In order to do this, the easiest way is to let q1 be 20, and if 2q is 10, then 2q2 is 20, then q1 equals 20, 2q2 equals 20, q1 equals 2q2. It all worked out. How much would these two bundles cost me in total? Well, I'd have 20 times $1 plus 10 times $2, be $40. That's your expenditure. You could say I can minimally expenditure reach this utility being equal to 20 utils for $40. How about this? Does this look familiar? Do you think we can use Lagrange on this, or should we look for other skills? Well, this is just poorly scaled Cobbs-Douglas. With Cobbs-Douglas, your alpha here and here would sum to 1. Instead, we have q1 to the 1, q2 to the 2, q2 to the 6. It sums to 7. It's not truly Cobbs-Douglas, but what happens if I zero out q1? What happens if I zero out q2? If I zero out either of these, I'm going to have utility equal to 0. So does that mean there's any potential for a corner solution? No. If I want to have positive utils, I need to have positive values for both q1 and q2. Unless, of course, you try negative values for q2. But let's assume for all problems all the time, no negative values for your goods. It's silly. So since we think this should be solvable via the Lagrange method, what is your Lagrange function? What are your FOCs? And why do you think tangency, if you can find it, is likely to find the solution? So work that one through. See if you can figure out what MRS equals MRT suggests. Let me know how it turns out, and I'll catch you next time. Bye.